Hello, this video is entitled Representation of Functions by Power Series, and also we'll talk about Taylor series. Now let's start with the geometric power series using the geometric series that we've already learned before. So let's start off, suppose we have f of x equals 1 over 1 minus x, excuse me. Can we represent that as a function? Now, if you notice, this clearly looks a lot like the geometric series, where r to the n from n equals 0 to infinity, the sum of that series is a over 1 minus r, provided that the absolute value of r is between 0 and 1. So if you try to model this 1 over 1 minus x to make it look like this, that would tell you that a would have to be 1, and r would have to be x. And then you can replace that in that geometric series right here. So you can put in 1 for a, x for r, and you are basically looking at 1 minus x being equivalent to the geometric series x to the n equals 0 to infinity. And here it's just kind of showing out a listing of the terms. Notice I did this in Maple. Now notice how Maple wrote this though, but it's just got a little negative to the outside. It's still equivalent because if you take the negative and you drop it down to the denominator, that would convert x minus 1 into 1 minus x. So it's the same thing, just written a little bit differently. Now we can expand this idea further. This is assumed centered at 0. Now you can talk about centering your function on certain values of x, which will affect your series. So let's say now we want to take this 1 over 1 minus x and we want to come up for the power series centered at -1. Now as you recall from power series, it's under the form x minus c, whatever your value is. So x minus a minus 1 would be x plus 1. And we're still trying to get it over into this a over 1 minus r bit here. But we have to do a little algebra to make this work. So what we have to do first and foremost is start with 1 over 1 minus x, and we have to replace x with x plus 1. And then, because that's what centered at -1 is going to mean, x plus 1. Now, it still needs to be minus between the two terms. So I've got to figure out what number, I have to solve for this value that will make this bottom expression still equal to 1 minus x. Now, what I did is I just came over here and I let y be my unknown here. So I'm saying 1 minus x needs to equal y minus x plus 1. And I got 2. So that's how I knew to put the 2 in right here. And you can easily check that, because whatever this is right here has got to be algebraically equivalent to 1 minus x. And it is. 2 minus x minus 1 would simplify down to 1 minus x. So that's the first thing you got to do, is you have to put in whatever x plus or x minus goes here. You figure out what number goes in front. Then there's one more step we have to do. Since we're dealing with a over 1 minus r, we have to make that number in front of the minus on the bottom. That needs to become a 1, if it isn't already. This case, it's not. This case, it's a 2. So we multiply top and bottom by 1/2. That'll convert it to 1. We're not worried about, and the 1/2 doesn't hurt us here with the x plus 1. We don't care about the 1/2 in the numerator. But that's very important, is that we have a 1 now. So now this expression here in red is what we need. We can convert that over to a divided by 1 minus r. That just means a will equal 1/2, and r will now be x plus 1 divided by 2, because it also needs to be multiplied by 1/2. So it's x plus 1 over 2. All right, so let's see what we have here. So that's what I just said, and that's written out. Now, to get the interval of convergence, being geometric series, whatever that ratio is, the absolute value has to be less than 1. So the absolute value of x plus 1 divided by 2 must be less than 1, which you can bring the 2 out of there. That's correct to do with absolute values. So you have x plus 1, absolute value of x plus 1 is less than 2, which then converts to this inequality right here. So you've seen this from back in the power series section when you were trying to find intervals of convergence. So we have negative 2 is less than x plus 1 is less than 2. Add negative 1 all the way across. So it's going to give you a negative 3 and leave you x in the middle because you're trying to solve for x. And you have 1 here. So that means this series that we're about to write here is going to converge negative 3 to 1. So we're going to put the a that we found and the r that we found into the a r to the n. So 1 over 1 minus x now equals 1/2 times x plus 1 over 2 to the n. So notice this power series still generates the 1 over 1 minus x like the one up here on the other page did. They're different representations, but they yield the same function. The difference is, okay, come on, here it is. Right here, yeah. That was the same thing, but it's a different series because it's now based on a different interval of convergence. See, the other one was based on negative 1 to 1. This one's based on negative 3 to 1. So you're not responsible for doing this, but what I did here is I took a couple of values, one that was within the interval and one that was without the interval, outside the interval. Negative 1.5, that's between negative 3 and 1. So, and you see it came up with 0.4, and so it came up with an answer. So which it should have done because it's inside the interval, so it converged. But I picked something outside the interval, like 1.5, and it gave us. Don't worry about that float thing. But the main thing is it gave us infinity, which is equivalent to saying it's going to diverge. Ironically, both of these values, the negative 1.5, would have diverged in the first example because that was on the interval negative 1 to 1. But negative 1.5 was fine here, but 1.5 was not. So let's try another example where it's centered at, it's 12 over x plus 3, but it's centered at 0. So we don't have an x plus, or like we did last when we had the x plus 1, we just have x itself. This is a little tricky because, we're modeling this over, the a over 1 minus r. So what we're looking at is, all right, we've got to have a minus down here. It's the first time we've had a plus here. Oh, don't want that. First time it's been a plus. Now we need it to be a minus. So to do that, I had to rearrange the terms. And so what I've done is I've written x plus 3 as the algebraic equivalent 3 minus x. That's still x plus 3. But it gets that minus in the middle that we need. So once we have the minus that we need in the middle, the next step is to turn that 3 into a 1. So I multiply top and bottom by 1/3. I get 4 over 1 minus a negative x over 3. So that means my a is going to be 4 and r is going to be negative x over 3. So I need that r, the absolute value of r, to be less than 1. So that's negative x over 3 is less than 1. So it's between negative 1 and 1. So now we have to actually solve this. And I believe do the absolute value, though. I probably could have just called this x over 3, but that's all right. But anyway, I'll leave it like this. And then I multiplied all three sides by negative all three parts by -3. And when you multiply or divide an inequality by a negative number, you must flip the arrows. So this became +3, that became -3, the arrows flipped, and then I just flipped the whole thing back around again. So now I end up with x being between -3 and 3. And that's going to be the interval of convergence. And then I wrote the series then. A was 4. I wrote this as -x/3 to the n. And look what it spit out here. 12 over x plus 3, so it was correct. Even though I mentioned you might have been able to change that to x plus 3, x/3, excuse me, don't do it, because I think it needs to be -x/3 here. Although it might have worked with x/3. Maybe I should try it real quick in Maple and see. I'll pause for a minute. Okay, I'm back. I used x/3, and that would not have been correct. I don't know why I thought I guess it was okay for solving that inequality, but it's not correct for the answer in the series, because it generates this answer, which actually is the same thing as 12 over 3 minus x, not 12 over 3 plus x. So that would have been wrong, but I guess even though it just wouldn't have affected the interval of convergence, that's all. But it absolutely affects this answer right here. All righty. Let's try another one. Here's another one with a plus, and now we're not centered at 0 either. So we're looking for a power series for f of x equals 5 over x plus 7, centered at 3. Now, this is a little tricky, but centered at 3 does mean x minus 3. But what I did here is I wrote this as 3 minus x. 3 would still make that 0. This is still okay. But here's the reason why I did this, is because, once again, I know it had to follow this minus sign. Like the last problem, remember, had a negative x. So that's kind of the rule on this. If it's going to be plus here, it's going to have a negative x. So this had to be minus 3 minus x. And if you want to solve this sort of the way that I did back up here, with this technique over here like that, if you want to solve it that way, you can. I just kind of looked at it and figured out what it kind of had to be. And then obviously if it was wrong, I could easily change it. But I said, okay, obviously if this is a plus 7 here, that's a minus 3. I said this has to be a 10. So in other words, 10 minus 3 minus plus x. So 10 minus 3 plus x is 7 plus x, which of course is x plus 7. So that's okay. So it can be a little tricky on the algebra there. You just got to, you got to have the minus in the middle, and then the bottom has to be equivalent to whatever you started with here. And then, of course, now once you get to this, that's the hardest part. This part's not too bad, because in this case, I just put that 10 there in red to sort of isolate it and show that's what has to be converted to 1. That's the only other number that has to be changed. So to do that, I multiply top and bottom by 1 over 10. I get 1/2 on top. Of course, my 10 becomes a 1. And then I have 3 minus x over 10. So it looks like I wrote the series first and then worried about the interval of convergence, which is fine. A is 1/2, R is 3 minus x over 10, so it would be n equals 0 to infinity, 1/2, 3 minus x over 10 to the n. And you can look over there to the right, you can see the Maple output. It gives me 5 over 7 plus x. So I probably did it correctly. Interval of convergence. So basically you just take 3 minus x over 10, put it between -1 and 1. I multiplied by -10, flip the arrows, change the numbers, and then I got x minus 3 is between -10 and 10. So I added 3 to all three parts, and I got -7 between negative 7 and 13. It looks like I didn't test any numerical examples on this, but where I could plug a number in, see if it worked or not. That's okay. We don't need to do that. Actually, it wouldn't be that hard to do because as a geometric series, what's in that parentheses has to be between negative 1 and 1. So you could tell real quickly. Now, we're not including these endpoints, keep in mind, but 3 minus a minus 7 is 10. 10 over 10 is 1. So it's not including that exactly. So we're saying between. And 3 minus 13 over 10 is negative 10 over 10, which is negative 1. And it's between those two. So that fits the criteria for a converging geometric series. And you didn't have to test that. But that's just sort of backing up that that would be the correct interval of convergence. And I don't think you have to worry too much about these operations with power series. I just kind of put some stuff in there. You can substitute with a power, kx, so kn, xn. Okay, not that big of a deal here. I use this last one, this third one. Now, I just thought this was interesting. I wouldn't anticipate putting this on an exam for any reason or whatever. Just kind of showing you the different ways you can go about, different ways, different techniques to construct this. This one, we would use partial fractions to break this down into two individual functions. And I didn't show the partial fraction work, but I showed the output. So you would have a let's see, 2 over x plus 2 minus 3 over 3x minus 1. Now, of course, that's with that plus. I needed that negative x, so I rewrote that as 2 minus a minus x. But what I did here, to reverse the 1 and the 3x, I just multiplied by negative 1 and made that a positive. So it actually got it right in the order that I wanted right there. It worked out perfectly. That to flip them around. Or either way, you pull out a negative, it's going to kill that negative and make it plus. In other words, I'm just saying this didn't have to be plus for any mathematical reason. It's just changing it from minus to plus made this be in perfect order right here. So it worked out beautifully. Then you actually end up within the sum of two geometric power series. So this one, A is 1, so there's nothing in front here. And R would be negative x over 2. So I have negative x over 2 to the n, plus this A is a 3, so we got a 3 there. And then that's 3x to the n. And then using kind of those algebraic properties above, I factored out the x to the n, which would just leave me a negative 1/2 to the n here. And this is going to be 3 to the 1 times 3 to the n, which will be 3 to the n plus 1. I'm not saying that had to be done. It were actually in this form right over here still correct. But I just thought it'd be interesting to get it into one series there. One nice compact series. And so I typed in my combined result right here, and look what it spit out. Exactly what it was supposed to, which we know that's already the fraction decomp. So this series correctly represents our original function of 3x minus 8 over 3x squared plus 5x minus 2, centered at 0. So it's kind of interesting just to see all the different kinds of techniques you can use to do these. Now, what I did for this one, for the interval of convergence, is I found the intervals of convergence for each one separately, and then the final result had to be what was in common between the two. Obviously, it's got to fit both. So in this case, the common one between these two is that one on the bottom, because that would encompass both of these. So it's a very small window range here from negative 1/3 to 1/3. Just for the heck of it, I put 0.1 in there, which is in that range. And then you see I got a converging answer right there when I put in 0.1. So, all right. So as I said before, I wouldn't worry too much about that kind of problem being on an exam. But power series, you can integrate and differentiate. It's kind of interesting. Or, by substitution. This is another one that's using one of these rules above. Now this one we're using 1 over 1 plus x. They're giving it to us right here. This would not have been hard to work out. Because you would have treated it as 1 minus a minus x. And you would have had negative x to the n. Well, negative x to the n is the same thing as negative 1 to the n times x to the n. So we're going to use that one, which is a slight variation on the regular geometric series. So suppose I want to represent 1 over 1 plus x squared as a power series. So what I'm going to do is I'm going to take 1 over 1 plus x and replace x with x squared. And that is absolutely acceptable to do that. It's not too difficult. So you see I just took that formula x to the n and replaced x with x squared. So now I just have negative 1 to the n times x to the 2n. Multiply exponents. So I don't know why I wrote it twice there, but that's okay. And then just for the heck of it, I put it in maple. And look what maple spit out. 1 over x squared plus 1. So that one really wasn't too difficult. Now, using that result from part A, could we come up with the series for arctan? And we can. Because arctan is the antiderivative of 1 over 1 plus x squared. Now I just put the plus c here, even though we don't need it for the series, but it would be that way in an integral. So all you do, we're going to integrate. How do you integrate this? Seems weird integrating a series, but you're just integrating the x part. N is like not a variable. It's like a number, numerical value, a constant, I should say. So you're integrating that as if 2 to the n was just a constant, was an exponent. So the negative 1 to the n would be there, so you just would do the regular power rule. You would integrate x to the 2n. Antiderivative would be x to the 2n plus 1 over 2n plus 1. That's kind of blurry. I didn't type that in Maple to verify it, but this is from a list of series I'm going to show you here in a few minutes. But there it is. You see, they're showing arctan. They're showing it as a Taylor polynomial expansion, which then forms this series. In fact, when we talk about Taylor series here in a minute, Taylor series basically just come from Taylor polynomial expansions. Okay. And there it is. You see it's x to the 2n plus 1 over 2n plus 1, negative 1 to the n. That's your series representation for arctan. Now, there's a pretty easy series to show here. I didn't write out all the work. I'll just explain it verbally. I don't ask anyone to derive this on a test, but it's not too difficult. I think I can explain it verbally without writing it out. A very basic series for pi can be represented by using that arctan series. Now, it's not a very powerful series for pi. There, as I mentioned over here in what I wrote right here, it's very basic, and there are other series for pi that converge much quicker and are better, but this is an easy example for us to look at based on what we're doing here. So now we know what arctan, now equals this series. I know the summation's not in front of it, but it equals this. Now suppose I replace 1. So I'm setting arctan of x equal to this right here. And I put 1 on both sides. In other words, the left side, I have arctan of 1. The right side, I put in 1 for x. Well, that just gets rid of all this. 1 to the 2n plus 1 is just 1. So that goes away. So you're just left with negative 1 to the n over 2n plus 1. And we almost have it because it's arctan of 1 is equal to pi over 4. Now I could just leave it as pi over 4 if I wanted to, but if I want to solve it just for pi, I'd bring the 4 up and over. So pi will then equal 4 times n equals 0 to infinity of negative 1 to the n over 2n plus 1. And look at the answer in Maple. Pi. I paused for a moment to bring up a couple to show you these are a couple of famous series for 1 over pi. So obviously then, 1 over that right side. And that's pretty scary. I'd love to see how they came up with that. Ramanujan. And then this one below, the Chodnovsky brothers. Yeah, this one I think is recognized by far the best one, but it's pretty crazy looking, but those are both better than what we did. But that's okay. I know it's way too confusing. The one we found was called the Leibniz formula for pi. Much friendlier, but yeah, it's pretty fascinating what's been discovered. But yeah, that one's the one they're just showing you. They'll get to pi a lot quicker and generate a lot more digits. But we found pi in a cute little way here. Let's take a look at differentiation. Now we just did one with integration. We'll do like a derivative. So let's say we want to represent this function, negative 1 over 1 plus x squared. That happens to be the derivative of 1 over 1 plus x. You can check that pretty easily. So we would take the derivative of this function we have right here for 1 over 1 plus x. We just take the derivative of it. So x to the n becomes n times x to the n minus 1, just using the power rule for the derivatives. Now, the counter is always going to shift here because, when you're taking the derivative, you're kind of, differentiating away that first constant term. Everything kind of shifts over. So it moves over to n equals 1. You can make it shift back if you want to. I think I mentioned that down here. There's no need to, but yeah, I've got it down here. I'll show you if you're just curious. But this is perfectly correct. You just have to make sure you just change that to 1. And notice that's what I have in Maple with it at 1, and that changes it to negative 1 over x plus 1 squared. Okay. All right. Okie doke. Let's see. Now part B is asking for 2 over 1 plus x cubed, which then happens to be the derivative of the one we just found. And so to represent 2 over 1 plus x cubed, we take the derivative again. So the derivative of nx to the n minus 1 will bring down an n minus 1, and we'll make the exponent n minus 2 now. So there's the n minus 1, there's the n minus 2, and you shift the counter over again, so it becomes 2. So starting this at 2, because like I said, you're differentiating away a constant there, so you're losing a term. And there it is. So Maple agrees with that answer. Now I'm sort of explaining here that if you wanted it to be 0, back at 0, for whatever reason, not important, but for the first one, you have to replace n with n plus 1, and then for the second one, you replace n with n plus 2 for each derivative term. So not necessary, but so I took the first one, replaced n with n plus 1. Remember, that was n minus 1, so you put in n plus 1, that becomes n. See, these just become, it's whatever makes this x to the n. That's what we're doing. So that's why it's n plus 1 here, and it was n plus 2 here, because remember that one was n minus 2. So that you put n plus 2 here, you get n plus 2. You Put n plus 2 here, you'll get n plus 1, and then x to the n. See, now I have them both starting at 0, and look what then they're yielding those answers. I'm not saying you ever have to actually do that, but I just wanted to point that out, that it could go, be rewritten again back at 0. All right. Let's see. Talking about Taylor and Maclaurin series. Maclaurin just means centered at 0. So once again, Taylor series are formed, off of Taylor polynomials. So here's a Taylor polynomial. And for a natural log of x centered at 1. So we've done this from the Taylor polynomial section. So these are all the derivatives. I don't think those need to be explained. I put in 1 for each one of those to get these values. 0 would be 1, -1, 2, and -6. And then we put it right in the Taylor polynomial formula. First one's going to be 0. Then we have x minus 1. And then we have a -1 over 2 factorial, so -1/2, x minus 1 squared. And then 2 here divided by 3 factorial, which is 6, 2 over 6, x minus 1 cubed, plus -6 over 24, x minus 1 to the 4th. Now I did reduce these, you don't have to, but I got rid of the 0. Reducing them. Now it can be kind of tricky. I don't think we're really going to have to do this too much, but if you were expanding one, sometimes it can be a little hard to generate the pattern, to establish what the pattern is to generate these. So I'm just letting you know in general, I'm not anticipating that you're going to have to do it, but because you have to take this and then figure out this pattern for the series here. Here's where they're reducing it, so here's what, and you kind of look at this, and well, you can see the x minus 1 is not hard to establish. So I'm starting at 1 here. We lost that first term. I could have made it work for 0, I guess, but not important. We're just looking for a correct representation. And I have x minus 1, and notice, see, that's technically x minus 1 over 1. So the denominators are 1, 2, 3, 4, like that. So they're just n. Starting at 1, so that was n, there's where the n comes from. And then now -1, n minus 1, I guess I could have done n plus 1. I just have to guarantee that I'm looking to whether it's positive or negative is the key. So n minus 1 or n plus 1 would have been okay. Well, anyway, since it's positive, n minus 1 makes that negative, starting at 1, makes that -1 to the 0, which will make it positive. Then when n is 2, you have -1 to the 2 minus 1, which will be -1 to the 1, which is -1, so it makes it negative. So that's how, you just have to play around with that to establish the pattern between plus and minus. And so I just verified that in Maple. So there it is. But so we just now took that Taylor polynomial that I might have just copied this problem right from 9.7. Might have been one we've exactly did before in that section, or whatever section number it was. But and then this time though we established the series pattern that went with it. Okay, now I'm just showing it starting at 0 if we wanted to. Still yielded ln of x. Now I'm doing it for sine. Okay, I think you're all right. I'll just kind of skip through this part a little bit here. Just kind of want to get to the part of interpreting the series. I'm sure you can do the Taylor polynomial, no problem. And notice this one, we're losing every other term here, aren't we? All right. So we're not every term is there. So what happens? We got this first term here. So we're going to have 1 times x centered at 0 makes it just x. 1 times x. Don't have the next term. We'll have the next term, which will be negative 1. This time I'm leaving the factorial in there because we're going to want factorial in our series. So it's negative 1, so it makes that minus over 3 factorial. We don't have the fourth term. We'll go to the fifth term, and then that's going to make, see, that's positive 1 right there. So it makes it plus, and then over 5 factorial. Now I have a plus here. Actually, that just means plus on, but the next one would have been negative. Plus does not mean it was going to be a plus term. So here's how I look at this. I said, okay, I tried starting it at 0, and you can think of, since there's nothing on the bottom, there's a 1, but 1 is also 1 factorial. So I'll start with the factorial. Like I said, you can play around with this. Let's see. I need it to skip by 2 every time, so that's where the 2n's coming from, to make it hop over by 2. You don't do n plus 2. That wouldn't really work. You need 2 times n. And you can test that, obviously. And then plus 1 to make it fit. And we can check that. If I put in 0, 2 times 0 plus 1 is 1. I put in 1. 2 times 1 plus 1 is 3. There's 3. Put in 2. 2 times 2 plus 1, 5. Okay, so it's establishing that pattern correctly. Notice the exponents are the same thing. So the x will just be raised to the 2n plus 1. That'll be okay. And then the negative 1's either going to be to the n plus 1 or n, or even n minus 1. And so it depends on where you start the n. But just to start determining whether it's going to be positive or negative. N will work here because we're starting at 0. So negative 1 to the 0 is positive 1. Then when I go to 1, negative 1 to the 1 will be negative 1. That'll make that negative. 2, negative 1 squared is positive 1, makes that positive. So I think we got something there. I didn't verify this in Maple, it looks like, but we're going to see that come up, it's going to be in a list of series here in a minute. Now let's think about this one. Suppose I wanted to find the Taylor series also centered at 0. Okay, I kind of told you what we're going to be doing. Pretend like we weren't going to, you didn't know that I didn't have the next line written there. Well, we could go through this same process like we did right up here. You know, take the Taylor polynomial terms, list them out, create the formula. Or, easier, is why don't we just use differentiation? Since we know that the derivative of sine is cosine, that means the derivative of the power series for sine will equal the power series for cosine. So how about that? That's pretty exciting. So we're just going to differentiate this. So I bring down a 2n plus 1 up here on the top. And then, of course, you subtract 1. That makes that 2n plus 1 goes down to 2n. And notice I'm automatically changed the starting point to 1. And then I simplified this because 2n factorial can be written as 2n plus 1 times 2n factorial. That just enabled me to algebraically cancel out the 2n plus 1s. So it's only left with 2n plus 2n factorial, starting at 1, which I could have reset that back to 0 if I wanted to, which is kind of interesting because the cosine is... All right, well, I changed it back to, or I guess it doesn't matter the 0 there or whatever, but I have 1, but I put it in there as 0. Okay, I'm saying here that it didn't have to change to n equals 1 for cosine, since this is a Taylor series and not a power series that's based on a geometric. That's when you have to change it. But so evidently it just didn't have to change to 1 right here. All right, it can be entered as 0. But that's what this series. So you see, it shows the one for sine right above it that we have, and then the one for cosine that we just found by differentiating the sine. So now let's take a look at this one. 2 sine x cubed. All right, smart way to do this would be take the series that we already have and substitute again. That's exactly what we're going to do. So the 2 you can just treat as a multiple. I'm going to replace x with x cubed. And then basically we have it. That's all we had to do. And then look at, so I just replaced the x cubed with x, put a 2 out here, and look what it gave us. 2 times sine of x cubed. So this is, we're using an existing Taylor series is your friend here, because if you had to generate this from a polynomial, I'm not even sure if I could have figured this out, because it would have got to see the pattern of the terms. You know, that would have been kind of difficult. I mean, I could have done these derivatives, even though it would have been kind of ugly, but look, here's what would have happened. So you would have had to do this if you were doing a Taylor polynomial for this. Okay, first one's just a chain rule. Okay, and then the next derivative will be a product rule. But here's where we're getting ugly in a hurry, is that then the next derivative is 2 product rules. Then the derivative after that would have been 4 product rules. And then we would have plugged the numbers in and tried to figure out the pattern. We might have been able to come up with, I don't know, I shouldn't say, that might have been doable. We probably maybe could have figured that out. I didn't put the 2 in front of this. I guess I forgot to put the 2, but obviously you just add the 2 in later, but it didn't affect this. But, well, anyway, just the derivatives would have been inconvenient enough. But we might have been able to figure that out. But anyway, not nearly as nice as what we just did. And here's a list of some common functions and their power series. You don't have to know these, and if I was ever to ask a question involving something to differentiate or do whatever, I would give you that starting series there to work with. So here's e, that's x to the n over n factorial. Here's sine and cosine that we worked with. Arctan, we talked about that one earlier. Arcsine's kind of an ugly looking one. Then we got a 1 over k raised to a power, so yeah, notice they have look, so here's 1 over x, here's ln of x. Well, since 1 over x is the derivative of ln of x, that means you could differentiate this natural log series to get that series right there. Well, although it's already given here, but I thought it was worth pointing out. So, yeah, so it's kind of an interesting little summary of series there, but don't worry about committing those to memory or anything like that. So, all right, that concludes this video on representation of functions by power series and intro to Taylor series.